Hello everyone. So this video is going to be going over alpha decay, beta decay, electron capture, and half-life. So we're just going to go through some practice problems, and you can pause the video as we go through them. So for all of these, we're doing alpha decay. So for the first one, we need to use the alpha particle. And we need to make sure that the atomic numbers and atomic masses add up on each side. So over on the left, we have a mass of 256 and an atomic number of 103. So in order for these to match on both sides, we would need to have a mass of 252 and an atomic number of 101. Because 252 plus 4 would give us the 256, and 101 plus 2 would give us the 103. And now we just need to look on the periodic table to see which element has an atomic number of 101, and that is MB. Okay, and for the next one, if we're doing another alpha decay, we're still going to be using the alpha particle with an atomic mass of 4 and an atomic number of 2. And in order to have the masses and numbers add up on both sides, so 231 minus 4 is 227, and 91 minus 2 is 89. And then again, we can just look on the periodic table to see which element has an atomic number of 89. And that would be A, C. Okay, so for the next one, just like before, we're still using the alpha particle. And for this one, 185 minus 4 would be 181, and 79 minus 2 would be 77. And the element with an atomic number of 77 is IR. Okay, and for the last alpha decay question, so 211 minus 4 would be a mass of 207, and 87 minus 2 would be an atomic number of 85. And the element with atomic number 85 is a T. Okay, so now we're going to be doing beta decay with these 4 elements. So first, we need to know what our beta decay molecule is. So for beta decay, it's going to have a mass of 0 and an atomic number of -1. And just like before with the alpha decay, we need to make sure that the atomic masses and atomic numbers on both sides match. So since the mass of the beta particle is 0, we're still just going to have a mass of 32. And since the atomic number is -1, we're going to have an atomic number of 16. And just like before, we need to look at the periodic table and see which element has an atomic number of 16. And that would be sulfur. And for the next one, we're still going to be using the same beta particle since it's beta decay. And just like before, the atomic mass will stay the same. And for this one, we're going to need to have an atomic number of 28 because 28 plus a -1 will give us that 27 on the cobalt. And then just like before, we can look at the periodic table and see which element gives us an atomic number of 28, and that would be nickel. Okay, and now for magnesium going through beta decay, we'll have our beta particle again. Atomic mass will stay the same. And our atomic number would be 13 here because 13 plus a -1 gives us that 12 on the magnesium. And the element with an atomic number of 13 is aluminum. Okay, and now for sulfur, we have our beta particle. The mass stays the same. And our atomic number here would need to be 17 because 17 plus the -1 from the beta particle would give us the 16. And the the element with a atomic number of 17 is chlorine. Okay. Now we will be doing electron capture. And for this, so previously for the alpha decay and the beta decay, we had the particles going on the right side of the arrow. But for electron capture, the electron is going to go on the left side of the arrow. And I'm just going to represent the electron like this. It'll have a mass of 0 and an atomic number of -1. And then just like the alpha decay and beta decay, we need to make sure the overall atomic masses and atomic numbers match on each side. So since the mass is 0 for the electron, we'll still have a mass of 14. And we'll have a 6 plus a -1 for the atomic number. So the atomic number would be 5. And we just need to look and see what has an atomic number of 5. And that would be boron. And then same thing for this aluminum. We'll have the electron with atomic mass of 0 and atomic number of -1. The 236 will stay the same, and the atomic number will go down to 12. And the element with an atomic number of 12 is magnesium. And now finally for the calcium, we'll have our electron on the left side of the arrow. The mass will stay the same, and 20 plus a -1 will give us 19, which would give us potassium. Okay, so for our final question, we have a half-life problem. So the half-life of plutonium-239 is 24,300 years. If a nuclear bomb released 8 kilograms of this isotope, how many years would pass before the amount is reduced to 1 kilogram? And these are the equations that we will need to use involving half-life. So it already gives us the half-life. So we can go ahead and plug that into our top equation. So we would have 24,300 equals ln of 2 over k. And now we can solve for k by multiplying k on both sides, which would give us 24,300 k is equal to ln of 2. And now we can divide 24,300 on both sides. So we would have that k is equal to ln of 2 over 24,300. And that comes out to be 2.85 times 10 to the negative fifth. And now that we have our k, we can plug it in to the bottom equation over here with the rest of the information in the problem that it gives us to solve for the amount of time that would pass before it reaches the amount that it's asking for. So n is going to be the amount that it was reduced to. So we'll have 1 equals, and the ni is the initial amount, which would be the 8. We have e to the negative k, which we just solved was 2.85 times 10 to the negative fifth. And then we have t, which is what we are solving for. So first we can divide both sides by 8, which will give us 1/8 equals e to the negative kt. And now we need to get rid of the e by doing a natural log of both sides. So that will cancel out the e, and we're going to be left with ln of 1/8 is equal to negative kt. And now we can divide by negative k on both sides to get the t all by itself, since that is what we're solving for. And now we can just plug this into the calculator. And so we would have ln of 1/8 over negative 2.85 times 10 to the negative fifth. And that comes out to give us a time of 72,900 years. Okay, thanks everyone for watching. That is the end of alpha decay, beta decay, electron capture, and half-life.